All right, Physics 3030, the universe. This is lecture 6, and today we'll be talking about particles and particle physics and what we need to know to talk about the early universe. We'll start with talking about the 4 fundamental forces, particles, and then we'll get to antiparticles. And the way we're going to organize this is we're going to run through it in a few different ways, but what I really want to talk about is this idea of the hot universe. Okay, when we think about interstellar space, we don't really think about a very hot universe, but what we've seen is that the cosmic microwave background radiation really lends itself to this hot universe idea. The cosmic microwave background and the Hubble expansion both point to a hot small universe. Okay, and hot universe, all right, so hot is really synonymous with high energy. Okay, and high energy is definitely the realm in physics of particle physics. A lot of you guys have heard about particle colliders and the huge amounts of energy that it takes to deal with particle physics. So that's really what we're talking about when we're talking about high energy. So to talk about the early universe, we need to talk about particles. So that's what we're gonna do. And we're going to talk about them in a number of different ways. We'll organize them in a number of different ways. And the first way that I want to talk about is talking about the 4 fundamental forces. And a lot of times you'll hear physicists call them not forces, but interactions. Okay. And the first of these that you're pretty familiar with already is electromagnetism. And I want to make a historical note here, which is that electromagnetism used to be just electricity and magnetism separate. And people knew about lodestones and using compasses for a long time. That's the magnetism part. People knew about electricity for a little while. Ben Franklin really is one of the first people to do a lot of research in it. But they became combined. Okay, they became combined by a man named Faraday. And Faraday really just put a compass near a moving wire and realized that the compass was changed, so the force of magnetism was changed by the electricity that was moving through the wire. And so he actually sort of figured out that there was some relationship between the two, and then a guy named Clerk Maxwell, who there's a set of equations called the Maxwell equations, which describe all of electromagnetism. He showed that he combined the theory into one theory and showed that the electromagnetic waves, so E and M waves, happen to move at our favorite velocity, c. And it was until the theory showed that electromagnetic waves moved at the speed of light, that it was realized that light is electromagnetic waves. That was the real connection there. And this is really referred to as one of the first unifications. So these guys were unified. And so this is one of the first unifications of forces. We knew about the force of electricity, the force due to magnetism. We realized, oh, they're really just the same force. And it depends on whether the charges are moving or not, whether you get magnetism or not. Okay. Now, electromagnetism has many of the interactions that we can think of. So, for instance, electrons around atoms really describe chemistry. Okay, so really, most of regular chemistry is electromagnetism. So that's everything that we eat. Okay, and things like your muscles moving, right? The force of your muscles is due to electromagnetism. Okay, the force that's keeping you from falling to the ground right now. So sitting in your chair, is also electromagnetism. It's the electrons in the seat of the chair, right? This is you sitting on your chair, sitting at the computer, okay? And what's really going on here is that the force on the seat of the chair on your bottom there has to do with those little electrons floating around, and those negatively charged electrons are repelling the negatively charged electrons in the atoms of your body. And so that's really where it comes. That's electrical force, the electrical force pushing you away. So we're pretty familiar with electromagnetism. It really is a lot of the different forces that we see throughout the course of a day. So that's the first force that I want to think about. Okay, I'm going to try a new trick. Let's see if I can erase the whole page. There we go. So the next force that I want to talk about is one that's not so familiar, maybe. It's called the strong force, or the strong nuclear force. Change that to an A. And the strong nuclear force is what keeps nuclei together, actually. And so the little bit of historical reference here, researcher, physicist named J.J. Thomson discovers the electron in, I think it's like 1897. Okay. After he discovers the electron and that there's some fundamental unit of charge floating around, they decide, well, there better be fundamental units of positive charge floating around. But then a guy named Rutherford scatters some little positively charged nuclei. They're called alpha particles, but they're actually helium nuclei. He basically shoots them at gold, and by shooting them at particles, he actually finds that there is a nucleus. And so all of the positive charge is concentrated at this nucleus. Okay, so all the positive charge is concentrated in this nucleus. But we knew that, two positive charges sort of repel each other, just like those negative charges I was talking about in the chair and your butt. They repel each other as well. And so why were these positive charges holding onto each other? Well, the answer is that if this blue arrow is the force of electromagnetism, there's a much bigger force that wants to pull them together and move them in the other direction, and that is the strong force. Okay. So the strong force is really the thing that overcomes this positive repulsion, and so it's a much stronger force. And we'll talk about its range and things like that in a little while, and why it took us so long to figure it out. That's the gist of what the strong force is. And then there's another force called the weak force, or the weak nuclear force. Okay. And the weak nuclear force is weaker than both the strong and E&M. Weaker than strong and E&M forces. And this is the interaction that really has to do with radioactive decay. And we'll talk a little bit about this, but basically radioactive decay is you're in some bound state where you have the strong force holding everything together, and the weak force basically allows particles to escape the strong force. And that sounds a little counterintuitive, but that's basically where the weak force comes in, and it has to do with the production of neutrons and how neutrons and positrons come together. We'll talk a little bit more about that. And then one more force that we're all very familiar with, and that's gravity. We've talked about it a bunch already. Okay, and this is the weakest force which is a little counterintuitive since the weak force is called the weakest force, but this is the weakest one. And it's actually why we know about it so well. You've known about this since you were a baby, right? When you're trying to walk, you're dealing with looking at gravity. And the reason is because it's so weak, we can, as humans, we can actually work against it. Now, if you actually tried to work against electromagnetic force straight up, then you would probably get a pretty big jolt of electricity. Now, there's electricity running in our bodies, and it's really weak, and it took us a long time to figure it out. But it's because gravity is so weak that we can stand up. I can jump in the air against gravity. And it is much, much weaker. And we'll talk a little bit more about that as well. Okay, so that's just a quick general overview of the different kinds of forces. And the next thing I want to talk about is, try that again. Is the particles that are involved with all of these forces. So we have a bunch of different particles out there, and really from the 1930s, 1920s through the 1990s we were finding more and more new particles, and we were trying to understand how they all fit together. Okay, so I'm going to run through the different forces again and talk to you about what the forces of what the particles of each of the forces are. So let's first talk about electromagnetism particles. Okay, and the electromagnetism particles are any particles with charge. Right? Now, something to keep in mind is that these particles are not mutually exclusive, right? I can have a particle that is involved with the strong force and the E&M force and the weak force and the gravitational force. Okay, so any particles with plus or minus charge, you will see with the you will interact with the electromagnetic force. Okay. Now, a very important thing. Remember when I was talking about those states where you have an electron sitting up here, maybe somewhere, and if it falls down in its energy state, right? So this is some change in energy, and it falls down to some new state here, right? Remember that it emits a photon. Okay, and I'm going to write the symbol for a photon. A photon symbol is this symbol right here, and that's a gamma. That's a lowercase Greek letter, gamma, and that's the symbol for a proton. As you've probably guessed, the E with the negative sign is the symbol for an electron. Okay, and it emits this photon, and what we've come to understand is that this little particle, this little photon particle, is what is a mediating particle, and the photon on at some level is how the force of electromagnetism is really seen in the world. When you look at how two electrons interact, it actually comes out that they trade photons, right? And I like to think of this is a decent analogy. I sort of like to think of this as you have two people, right, and they're sort of playing ball with each other, okay? And as the two people are playing ball back and forth, they interact, right, by trading this ball back and forth. And that's exactly how the electrons and the protons and anything with charge, in fact, interacts with each other, is by passing particles back and forth between them. Okay, and these have a name, and any particle that is one of these particles that gets traded back and forth is called a mediating boson, or for our sake, mostly just boson for short, but there are different others. There's some other bosons out there, and the boson for the mediating boson for E and M is the photon. Okay, so the photon is the big guy, the one that gets traded back and forth. Okay, and that's how these particles interact with each other. And of course, there are good examples of particles that undergo the that take part in the electromagnetic interaction. And we already wrote down the electron. There's the positron, and anything else with charge. Okay, and then there is the weak force. Okay, and the weak force particles. There are actually 3 mediating bosons, and they're called the W and Z particles. And there's 3 of them because there's a W plus, a W minus, and a Z naught, which the Z naught has no charge, so it doesn't take part in the electromagnetic interaction, right? But since both of these have charge, they both take part in the electromagnetic interaction as well. But these bosons actually are massive, whereas the photon has no mass, right? So up here, I should definitely talk about this. No mass. The photon doesn't have any mass, so it moves at the speed of light. And if you know anything about relativity, which we'll touch on in a little while, you can't really move at the speed of light unless you have no mass whatsoever. These guys, on the other hand, they're massive, and that actually has a lot to do with why the weak force is a very short distance force. Not why it's such a weak force. That's partly because of the mass of these things, but it's more to do with the short distance effect. The weak force is a very short distance force, and it has everything to do with this mass. Because these guys have mass. Okay. And the weak force particles, are the electron and the quarks, which make up the proton. So there's quarks, which I'll talk about in a second, and the proton, which is really made up of quarks. And then, of course, the bosons, and then these things called neutrinos. Now, this isn't a V. This is another Greek letter. You're just going to see a few more Greek letters. And this is a neutrino, and now there are different kinds of neutrinos. Let's call this one an electron neutrino, and we'll talk about those as well as we keep going here. And these guys take part in the weak force as well, and they interact with the electrons and things like that. Okay. And then, in fact, the neutrinos really only interact weakly. They don't interact with E and M force because they have no charge, and they do not interact with the strong force either. Okay, and so the strong force particles you've probably heard about, and they are the quarks. Okay, and there are 2 different ways in which we see quarks. Quarks are never seen alone. You either see 3, and those are called baryons. Bary kind of refers to heavy baryons, and this is things like the proton and the neutron, and other exotic particles. There's things called the psi particle and all kinds of other big particles, sigma particles and things like this. They just start making up Greek names for these things. And really what it is taking the different types of quarks. Okay, there are 6 quarks. There's actually 6 different types of quarks, and mixing and matching them, right? The simplest ones give you protons and neutrons, and then if you get more exotic ones, you get these exotic particles. Okay. Or the other way that I can see quarks is by seeing 2 of them together, and those are called mesons. And mesons, mes means middle, so they're sort of middle-sized things, and there's things called K-mesons and all kinds of other names as well that you might see. And but we had to mostly make these. We only see these in really high energy places. And this is actually a quark with an antiquark, which I'll talk about in a little bit as well. We'll talk when we get to antiparticles here in a second. So there are 6 types of quarks, 6 types of quarks. But then they have bosons, right? So there are boson. The boson of the strong force is what's called a gluon, which is a not very creative name for what glues the quarks together. And there are 8 kinds of gluons, and we won't talk about the different names of gluons because there's too many of them, and it has to do with something called color. And your book talks about this a little bit, but we'll spare you the details right now. But there are 8 types of gluons to consider that get traded back and forth between the quarks. Okay, and these also are massive. So the gluons have mass as well. Okay, and so again, this implies that this is a short distance force. Okay, and I'm going to give you the details of that in a second of why that actually is. Okay, and then there is one more kind of force, of course, and that is gravity. So let's talk about gravity up here. So the gravity particles. And I'll tell you what, particle physics doesn't concern itself much with gravity, actually. Because gravity is so weak, we don't talk about it too much. But really, anything with mass, any particle with mass, will interact gravitationally. Okay, so anything with mass, will interact gravitationally. And there's something called, but then of course, so there's anything with mass will interact, but then there's the boson of the gravitational interaction, and that is called the graviton. But the graviton, it's really important here it has not been found. We've never seen a graviton, and the reason for that is that because the gravitational force is so weak, because the gravitational force is so weak, we've never really been able to find one. We're not even really sure there is one. Everyone postulates there is one. This really, it goes into the realm of quantum gravity, which we will be talking about later in the course, and I'll talk a little bit about that later. But for now, the stuff that we're going to deal with in the early universe, we don't need to really think about the graviton or this gravitational interaction. Okay, and then there's one more boson that I just want to talk about just for a second here, and that is the Higgs boson. So let's see if I can. I like that trick. Higgs boson. Now this has to do something with mass, and it is massive, so it actually has mass, but it's also supposedly, there's a mechanism for giving mass to the particles. Okay, so in the earliest versions of particle physics theory, most of the particles didn't have mass, or you put it in ad hoc, you just put in what the mass was. But the Higgs is the particle that gives mass to the particles. And the idea is that it's just this huge Higgs field that kind of sits around someone, right? So if I'm a particle and I'm moving through a room, and I just can keep moving through the room because there's nothing in the way. But if the Higgs field is something that it's just a bunch of little, they're actually pretty massive, but they work on a really short scale. And those particles are interacting with this one in such a way that it sort of slows the particle down. Okay, and it can only move so slowly because there are these other particles that it's interacting with. They're not necessarily trying to slow it down, but there's just so much interaction going on that it slows it down. And so whereas this particle that doesn't see the Higgs field, this one up here doesn't see the Higgs field, it can move at c. It can move at speed of light, whereas this one has to move less than c. Okay, and so the Higgs somehow interacts with these. So it's this idea, this theory, that you have this Higgs field that interacts with particles in such a way that it makes them seem like they have mass. Okay, and the Higgs boson is also unfortunately called the God particle, which is definitely a little bit of a misnomer, right? But this is the thing that they're looking for in this is the big particle that they're looking for in the LHC, which we'll talk about maybe next lecture, actually. So this is the Large Hadron Collider in Switzerland. So this is the particle that they're looking for, and it's very massive. It's heavier than any of the other particles that we've seen or talked about yet so far. All right. So that's sort of the list of particles by interaction. And again, the Higgs boson is really its own interaction. It's completely separate from those other forces. But it has something to do with the mass. And the last one that I want to talk about, actually, let's see, is let's go through this slide first, actually. Then I'll talk about antiparticles. So this is sort of a chart of the elementary particles, right? So we have a couple of other ways of categorizing them. Okay, so the quarks are, first of all, that's this block here, okay, are the quarks. And these guys, the up and down quarks are what make up protons and neutrons. Neutrons. And then all of the other ones are made by, this is the charm quark, the strange quark, the top and the bottom quark. Okay, and the top quark was only found in the 90s. So it had been predicted for a while, but it wasn't found until the late 1990s. So this is pretty new science, actually, in a lot of ways. Okay, so those are the 6 quarks. And then over here you have the force carriers. And so we've got the 2 kinds of weak carriers are the Z boson and the plus and minus. There's a plus and minus W. The gluon, which is the interaction for quarks, and then the photon, which is the interactor for the electromagnetic interaction. And then we have these things called leptons, and leptons are all weakly interacting. They do not interact with the strong force. They do interact electromagnetically. Okay, and then they're listed in generations just like the quarks are. And this is the simplest ones that we see, which is, of course, the electron, which we've known forever, and the electron neutrino, which is sort of its partner in the weak interaction. And then there's something called the muon, where mu is like a U with this front tail in the front, and that's another Greek letter. So muon. If you haven't picked up on it by now, right, the ending on is synonymous with a particle. So for a while, when people were naming particles, they just picked a Greek letter like mu and just added on. So that's muon. They just named it the muon. Okay, and then the T is a tau, so that's a tauon. How do you spell that? Tau is spelled like that, so let's just add it to that. Tauon. Okay, so that's this one, and this is heavier. So you sort of get, just within the pink and the green here, stuff gets heavier as I go from left to right. And the tauon has its own neutrino, the muon has its own neutrino as well, and those are all called leptons. So it's just a kind of another way of organizing it. And this is really what's known as the standard model of particle physics. Okay, and this is all of the particles that we know of and see all the time. Okay. All right. And before we talk about antiparticles, one more thing that I want to talk about is the sort of strength of these forces. So I'm going to just draw a table here. So I'm going to, on this side, I'll write the force. Here I'm going to tell you what the relative strength is. This is in your book as well. Okay, but I want to talk about it a little bit more. And this is the range, so the distance range that these guys really act on. Okay, and I'll write them from strongest to weakest. So we'll start strong, E&M force, weak force, and gravity. I want to put some numbers to this because I really want you to understand how much different they are. So relative strength, we'll call the strongest one have a strength of 1. Okay. If the strong force has a strength of 1, the E&M force has a strength that is 137th of that, of the strong force. The weak force has a strength that is 10 to the negative 5th, which is 1 over 10,000. Okay. 10,000? Let's see. 1, 2, 3. 1, 2, 3, 4. Nope. 100,000. 100,000. So 1 over 100,000. That's the strength of the weak interaction. And then gravity has a force that is even smaller than that, right? So gravity is 6 times 10 to the negative 39. There's no way I'm writing out 39 zeros. So it is 1 over 10 to the 39 the strength of the strong force. Very, very small. Much, much smaller than any of these. And you can see sort of that these three, compared to the gravity, are sort of in the same range. And that's why they are all working on some at the nuclear level. Now, there is an equation we talked about before. I think we definitely talked about the 1 over r squared idea. And we know that the gravitational force and the strong force go like 1 over r squared. And it turns out that all of these forces go like 1 over r squared times a decaying exponential, which if you're not familiar with an exponential, it is if I looked at the graph of it over here, right? A decaying exponential goes down and it goes so close to 0 so quickly that it's really hard to even see. Okay, and that starts at 1. Okay. And it all depends on that m, and that m is the mass of the mediating boson. Okay, and that mass has everything to do with what the range of these things is and what kind of range they work at. And so if I look at the range, let's fill this in a little bit differently. The E&M force is infinite, and gravity is infinite. They drop off like 1 over r squared, but you never really see where a spot where you can't see it anymore. The strong force and the weak force, though they're really, especially the strong force, which is really interesting, though it's really strong, its range is only 10 to the negative 15 meters, which is about the diameter of a nucleus. Okay, and that's not an accident, right? It's not an accident that's about the diameter of a nucleus. And then the weak force is even on a smaller scale, 10 to the negative 17th, so 1/100th the size of the strong force. Okay, so they work on very, very small scales, even though the strong force, and in some intuitive way it makes sense, right? It can be really, really strong, but it can't be strong over a very large area. To me, that sort of makes sense. But notice that the lines here, the relative strength increases as I go down. Right? This is relative strength is sort of increasing here. But the range doesn't do that, right? It jumps all over the place. E&M and gravity are infinite, and then these guys have much smaller scales. And that really has to do with the mass, as I talked about down here. Okay. So let's go to the next slide. And I sort of want to start with this picture here. This picture is a picture of a particle antiparticle interaction. And antiparticles They're predicted by quantum mechanics, and they're actually predicted by melding quantum mechanics with special relativity. Not general relativity, but just special relativity. And we'll talk about relativity later. And if you do that, a guy named Paul Dirac actually predicted the appearance of an antiparticle. And the idea was that it was a particle with the same mass but sort of opposite properties. So like opposite charge, say opposite electric charge. So there's something this is the first one that was actually found, was something called the positron, which is, the symbol is E+, and if you can guess from the symbol, it's an electron. It's the antimatter particle of an electron, and that's what's pictured here. And what we've found out since Dirac predicted this, right, was that when you have, so the sort of known thing, if you've ever watched Star Trek or some other sci-fi, is that if you have a electron and a positron and they collide with each other, they actually give off pure energy in the form of light. Okay, so you get off a couple of gammas here, a couple photons like this, and that's why there's a little bit of light coming straight off of that thing, right? But it turns out that this picture could be for the opposite interaction, and the idea is that it could also have light either colliding with itself, or it doesn't need to collide with itself. Actually, it could just come because it has so much energy. And from the light itself, I can get particles. Now, this sounds like a crazy idea, that something that has no mass can give me something with mass, but remember, these electrons have some energy. Okay, and Einstein tells us, you guys have probably all seen this equation, but this is really where it starts to come into play, that there's some relationship between the energy and the mass. And what the idea is the energy of these photons can actually be turned into mass of these antiparticles, the antiparticle pair. Okay, and this is, the left side is called pair annihilation. And of course, this side is called creation, and we can go in both directions here. And you can read a little bit more about particles and antiparticles and things like that, but I'm not going to go into any more details really than that, except to know that these reactions can happen like this. That's the most important thing at this point that we talk about. Okay, and all of those particles that I showed have antiparticles. So there's antiquarks and things like that. Except, this is really important if you haven't guessed, except the bosons, except those intermediate bosons. And those don't have antiparticles. Okay, so it's all of the things that sort of make up the matter, not the ones that are exchanged in between. Okay, and I think that's all we need to talk about really for antiparticles. And I just wanted to, think that there's one more last thing to talk about, and I want to just touch base again with the neutrino. Okay, and so just one last snippet here. The neutrino is a weakly interacting particle. I want to touch base again with it here because it'll become very important later on. And remember that if there's an electron, there's some electron neutrino. If there's a positron, then there's actually there's a sort of what you could call a positron neutrino, or this bar on it, I would say this is an anti-electron neutrino. It's another way of saying it, right? So I could call this a positron, or I could call it an anti-electron. People say anti-electron neutrino if you see the bar on it. And that'll become important in some reactions, and specifically decay of neutrons. Now remember, neutrons are baryons, so they're heavy. They're actually made of 3 quarks. Okay. And neutrons decay. They have a decay rate, a half-life, on the order of 8 minutes. So after about 8 minutes, you start losing a good chunk of your neutrons. In the decay process, the reaction goes like this. You get a neutron, you get a proton, okay, but the neutron is neutral, that's why it's called a neutron. And so you need to make sure that the charge is balanced on this side. So you actually get an electron. So the neutron decays into a positron and an electron. Now, this is not the end of the story, but what happened is in the 1930s, people were seeing this decay. And if you looked at the energetics of it, you found out that momentum and energy were not being conserved. Because what you can look at is the speed of the proton and the electron as it comes out, the speed of the neutron as it goes in, and everything should match up, and it wasn't matching up. And so Wolfgang Pauli, famous for the Pauli exclusion principle, surmised that, oh, maybe there's some particle that we don't see. And it turns out now we know it's a anti-electron neutrino. And there's some particle we don't see that's also shooting off and has some momentum with it. And so this is where sort of the neutrino came out, where we started seeing it. It's so weakly interacting that it's very difficult to actually be detected. It took, I think your book, I forgot exactly what your book said, but it took decades after being predicted to actually see it in an experiment. Okay, so I just wanted to talk a little bit more about the neutrino there, because we're going to touch base with it again here shortly. Okay, so that's sort of the general overview of particle physics. I know that at this point it sort of seems like I'm just giving you some sort of taxonomy. Okay, there'll be some outside reading. Your book is actually pretty good about organizing it. It hasn't organized it quite the same way I have, so maybe that will help. And there's lots of other places to look out there, and I will post a poster that talks a little bit about this stuff as well. Okay, so I'm going to leave you there, and thanks for your attention, and I will see you next week.